Welcome to the statistics learning session. In this session today, we'll explore application of Donsko's theorem. Donsko's theorem to statistical testing and random variable generation. The process highlights necessary critical highlights to pivotal distributions, the significance of universal critical values, and efficient generation of random numbers based on given cumulative distribution function. So let's get started. So first step is to understand the objective of Donsko's theorem. Donsko's theorem is used because it tells us that asymptotically, asymptotically what? What is just asymptotic? Can you tell me? Think about it. It tells us asymptotically that square root of n and fn minus f naught will converge to supremum of absolute value of Brownian range, which is a pivotal distribution. Which is a pivotal distribution. This distribution does not depend on unknown variables. It helps in building a test. Now, for this, obviously, when we are building a test, we need some critical values. To create a test, we need critical values that can be referenced universally. These values must be independent of specific distribution of f naught being tested. Pivotal distribution Tn remains the same for any n and any distribution f, any distribution fn, and for any distribution fn equal to f naught. Now, how do we generate these critical values? Can you think about it? Critical values are calculated or can be generated computationally for any test, regardless of the distribution. Example. Example. Example tests include f naught being a standard Gaussian, uniform on 0 and 1, or exponential distribution. So what are key insights we can get from this? Think about it. Key insights we can get from this are critical values are always the same for supremum of absolute value rounding range. Although this might not be evident initially, certain methods confirm this. Now let's work on a certain method. We'll take a CDF F create a random number generator. Now we'll try to create a random number generator from the CDF. How do you do this? Think about it. To generate as data from CDF, well, let's start with the U, a uniform distribution, which is uniform between 0 and 1. And now we'll compute whatever the random variable x by using f minus u. So that's it will produce a random variable x. Now we'll compute x by inverse of f minus u. What I'm saying is that fx will produce it's a uniform distribution. Now, whatever this x we are inputting, we can say that it is f minus 1 u 0 1. Now we can find out what we inputted into this function. It will give us some random variable. While this method works, proof. For the proof, let's say that px is less than t, then we can say that p f minus 1 u is less than t. Then we can say that p u is less than ft, which is equal to ft. The CD of x matches f demonstration correctness. Properties of general random variables. Let's talk about that. Applying fx, applying fx produces, what is it produces? It produces a uniform distribution which is 0 and 1. This property holds universally, even pseudo inverse functions. CGF, let's talk about CGF proof for fx. Showing uniformity of fx. Now let's compute the probability of pfx t equal to px f minus 1 t equal to f minus 1 t equal to t. Fx is uniformly distributed on fx. So fx is uniformly distributed on 0 and 1. Let me summarize what we learned today. This presentation explains the asymptotic behavior of pivotal distribution derived from Donsko's theorem and the methodology for generating random numbers with any desired CDF. By leveraging universal critical values and computational techniques, statistics testing becomes flexible and efficient across diverse distributions. The outlined methods ensure both theoretical soundness and practical applicability. That's all for today. I will see you next learning session. Thank you so much. Have a nice day.